everyone. In this video, we're going to talk about converting between radian and degrees. We're going to talk about arc length, sector area, and a little bit about linear and angular speed. So let's get started. So first of all, let's kind of review. We know that pi over 2, 3 pi over 4, they're all radians that we've taken from our unit circle that we derived in another video. And just keep in mind that these values around this circle we find them by kind of finding the circumference of the circle by wrapping a number line around the edge of the circle and measuring. So the measurement from 0, from this point here to here, would be pi over 6, and so forth. The definition of a radian is the measure of the central angle, theta. We call that angle theta, that intercepts the arc S, and S is what we label the arc length with, equal in length to the radius of the circle. And if we were to solve that to find our angle would be the arc length divided by the radius. Now with your unit circle, the radius was always 1. So all of these arc lengths, like pi over 6, if I divide that by 1, I just get pi over 6. So for the arc length on the unit circle itself would be just the same as the angle as that radian. So like here, that would be pi over 6, and then here we'd have pi over 4, and so forth, because we're only dividing by 1. But if we were finding the angle of a circle that has a radius other than just 1, then we have to divide by that radius. So here's an example that we have. What is the measure of the angle in radians that intercepts an arc of the length pi over 3 with a radius of 5? Now, just to kind of put this in perspective for just a moment, if you think about that unit circle, I'll just draw a quick little graph over here. That unit circle crosses the x-axis at 1, -1, and crosses the y-axis at 1 and -1. So we have this little circle right here, just like that, with a radius of 1. Okay, pi over 3, which is the value we're looking at here, on the unit circle falls like right in here somewhere. Okay, but for our example, now we're looking for a radius of 5. So if you can imagine, that would be a much larger circle. Like if I measured out 5 units, that'd be 1, 2, 3, 4, kind of way out here, just kind of estimating. That would be like a much larger circle like that, okay? So with that circle, that larger circle with a radius of 5, if I measured the same distance, like this pi over 3 from here to here, see how small that is? On this circle, probably would fit somewhere in here instead, okay? Would not go all the way to there, a distance of pi over 3. It would just kind of be like that. So if you look at it closely, this angle here is not going to be the same measurement of whatever angle is formed from measuring out pi over 3 on a bigger circle. So this angle like this is going to be like much smaller than this angle here, okay? So just to kind of put that in perspective. So let's get back to our problem. So let's find that angle. What is that angle that's going to give us an arc length of pi over 3? So theta equals pi over 3 divided by the radius, which is 5. And remember, when you divide with fractions, you multiply by the reciprocal of the denominator. So we got pi over 3 times 1 over 5, which is going to give us pi over 15. So the measurement of that angle is going to be pi over 15 radians. Okay? Now, before we go any further, let's talk about converting degrees and radians, because we'll have to make sure that all of our angles are in radians. And while we're at it, we're going to convert from degrees to radians as well. All right, so keep in mind that pi equals 180 degrees. And if you remember this fraction, that will help you every single time. So if you can't remember anything, just remember pi is the same as 180 degrees, and we can set up a proportion. Pi is radians, and 180 is in degrees. And if you set up that proportion and you just plug in, then you can solve any of these problems. So for the first example, we're going to take 2 pi over 5, and we're going to convert it to degrees. So I'm going to plug in 2 pi over 5 for my r. So I get pi over 180 degrees equals 2 pi over 5 over degrees. Now I'm going to multiply by d. I'm going to multiply by d. I get d times pi over 180 degrees equals 2 pi over 5. And now to get d by itself, I'm going to divide by pi over 180 or multiply by the reciprocal. So I get 2 pi over 5 times 180 degrees over pi. And if you notice, the pi's cancel out, right? And I love to reduce fractions before multiplying, because to me that just makes life so much easier. So we're going to take that 180 and we're going to divide that by 5 and we get 36. So now 5 goes into 180 36 times. So now we have 2 times 36 degrees, which gives us 72 degrees. So our degrees will be 72 degrees. Now I will say you can do this a little bit easier by just plugging in 180 for the pi. And I just want you to see that you'll get the same answer if you do it that way. You could say 2 times 180 degrees divided by 5 is the same thing that we got here. Honestly, the pi's canceled out the first way that we did it, and we ended up with 2 times 180 divided by 5. 5 goes into 180 36 times, and that still gives us 72 degrees as our answer. Okay, now let's convert from degrees to radians, the other way around. So what we're going to do is we're going to take 125 degrees and we're going to plug in for our d. So we get pi over 180 degrees equals radians over degrees. And now solve for r, we're going to multiply by 125 to have 125 degrees pi over 180 degrees, and that's going to equal your r. And the degrees cancel out, so those no longer there. And all I do from here, y'all, is I just reduce that fraction. So I know 125 is divisible by 5, and so is 180. So I'm going to take the 125 and the 180, and I'm going to reduce that down by dividing them by 5. And so 125 divided by 5 is going to give me 25 pi over 36. And that is going to be my radians. And that is how you convert from degrees to radians. Okay, so now let's use this in some examples. Okay, so the arc length of a circle is going to be the radius times the angle. And remember, the angle has to be in radians. And earlier we said that the angle was the arc length divided by the radius. So if I just rearrange this equation, that's where this comes from. So your arc length is going to be the radius times the angle. So let's look at our first example. A circle has a radius of 27 inches. Find the length of the arc intercepted by a central angle of 160 degrees. Well, the first thing we want to do is always convert our angle to radians. So I need to find out what theta is. So just keep in mind we can do our proportion. We can say pi over 180 equals my radians over 160 degrees. So I'm going to multiply by 160. So I get 160 degrees pi over 180 degrees, and that's going to equal my radians. Now all I have to do is just reduce that fraction. So let's see, 160, what's that? We could divide that by 20. So that'd be 8 pi, and 180 divided by 20 is going to give us 9. So we get 8 pi over 9, and that is our radians. So theta is going to give us 8 pi over 9. And our radius is 27 inches. And now all we have to do is plug in. So we're going to say arc length equals our radius, which is 27 inches, times our angle, which is 8 pi over 9. And I just love reducing fractions. Y'all know I love fractions. So 9 goes into 27 3 times, and 3 times 8 gives us 24 pi. And don't forget our unit, 24 pi inches. Okay, and there you have it. Now, I'm fine with you keeping the answer. This is in exact form, but you can put it in the calculator and find the decimal equivalent. Okay, so let's go to the next example. A circle has a radius of 15 inches. I'm going to go ahead and write that down. Find the length of the arc intercepted by a central angle of 65 degrees. So again, we have to change 65 degrees to radians. So we'll have pi over 180 equals radians over 65 degrees. Okay, let me erase this. And now let's solve. We'll multiply by 65. So 65 pi over 180 degrees equals r. And let's see, 65 divided by 5 is what, 13? So 13 pi over 36 equals our radians, and I don't believe that reduces any further. No, it doesn't. So that's going to be our theta. So theta will be 13 pi over 36. Okay. And now we're going to find our arc length. So S equals our radius times our angle, 13 pi over 36. The only reducing I can see here is that 3 goes into 15 5 times, 3 goes into 36 12 times. And so we end up with 5 times 13, which is 65 pi over 12 inches. And there you have it. Now, to put that in perspective, if you really want to see like what that equals, you could put it in the calculator. And so let's do 65 times pi and then divide it by 12. Gets you roughly like around 17 inches. Okay, so just kind of put that in perspective. All right, let's look at another example. Make sure, yep, that's it. All right, so now we're going to talk about linear speed and angular speed. Linear speed, we usually use v for velocity, okay? And that's going to be your arc length divided by the time. And we already know how to find arc length. We've talked about that previously. Angular speed is the speed of the angle, and we use this W looking thing, it's a Greek letter, to represent the angular speed, and that's going to be the central angle, our theta, divided by time. Okay, so let's look at an example. The second hand of a clock is 10.2 centimeters long. So that's the second hand right here. Okay, find the linear speed of the tip of this second hand as it passes around the clock face. So we're looking at the linear speed. So we're going to find V, which equals the arc length divided by time. Well, we have to find the arc length first. So we know arc length is the radius times the angle. Now, y'all, if this second hand moves around the clock, all the way around, one full revolution, that angle is going to be 2 pi. So that's what we'll have for the angle is 2 pi. And we know the radius they gave us was 10.2. So 10.2 times 2 pi, that's going to give me my arc length, which is going to be 20.4 pi. So let's plug that in over here. Arc length is 20.4 pi divided by the time, and when it goes around the clock, the second hand, that takes 1 whole minute, which is 60 seconds. And I actually forgot to write my unit here. That would be centimeters. So we're going to end up with centimeters per second. Now for this case, I would say put this in the calculator. So 20.4 pi divided by 60, which gives you roughly 1.0676. Okay, and let me try that again in my calculator just to make sure. 20.4 pi divided by 60. I think I had a rounding issue there. So it's 1.068. We'll round that 3 places. Okay, there we go. And centimeters per second. Okay, all right, on to another example. Now we have a wind turbine. The blades of the wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. Find the angular speed in radians per minute. So keep in mind, angular speed is the central angle divided by time. So we're going to have angular speed equals, now the central angle, think about it like this. There's 15 revolutions. One revolution is 2 pi. So that angle is going to be 2 pi times 15, which gives us 30 pi. So that is your central angle, 30 pi per minute. Okay, so that would be 1 minute. And so y'all, it's just going to be 30 pi radians per minute. And there you have it. Okay, now let's find the linear speed of the tip of the blade. So we know a linear speed is going to be the arc length divided by time. So let's find the arc length. S, I'll write this down, S over T. So let's find arc length, which is the radius times theta. We know theta is 30 pi. The radius is 116 feet. And I'll add my units in just a moment. And I would say use a calculator for this to calculate that. 116 times 30 pi, which is going to give us a rather large number, 10,932.742 feet. Okay, now we're going to take that, divide it by time, and actually the time in this case is per minute because it goes 15 revolutions per minute. So the linear speed is going to be 10,932.742 feet per minute. And there you have it. Okay, last thing, area of a sector. If you're finding area of a sector, it's going to be 1/2 times the radius squared times theta. Now, y'all, if you remember the area of a circle, area equals pi r squared. Well, basically that's the same thing. This would be area of a whole circle. Well, with the sector, that 1/2 theta is what takes the place of that pi. All right, so let me erase that. Okay, a sprinkler of a golf course sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. So can you imagine the sprinkler, right? And the water is shooting out. This is 70 feet. Okay, and as it circles around, it's spraying the water, and it goes like a 120-degree angle. Okay, so we're going to find the area of that sector. So kind of think of that as being 120 degrees. Okay, so area equals 1/2 the radius squared. And again, our angles always have to be in radians, so we're going to convert. It's 120 degrees pi over 180. If you do your proportion, that's what you'll end up with. And we can reduce that down. Let's see, what? 20, 120. Actually, they're divisible by 60, aren't they? So that would be 2 pi over 3. Okay, so we get 2 pi over 3. Okay. 70 squared is 4,900. Times 2 pi over 3. And we're just going to calculate that. So put that in the calculator. 70 5 times 2 pi divided by 3, and we end up with the area of the sector is 5,131.268 feet squared. And there you have it. That's how much area is covered by the sprinkler. I hope this video helped. I'll see you next time.